MacDonald, who's Professor of Neurology and Translational Neuroscience at the Center for Clinical Brain Sciences at the University of Edinburgh. He's also head of neurological diseases and stroke at the NHS Forth Valley site. His research interests include clinical trials in stroke, systematic review and meta-analysis of experimental in vivo data, and together these drive a third interest in evidence-based translational medicine. Malcolm's title is Using Evidence to Inform Translational Medicine. Malcolm MacDonald.
Well, thank you very much, and thank you to the organisers for having me. It's a particular pleasure to be here because about 25 years ago, when I was a neurology trainee in Edinburgh, I was desperately trying to work out what to do, and then found this book by the man in whose name we are gathered together, which was slightly too big to fit into a white coat pocket, but served me well and opened my mind to the idea that simply doing what my bosses told me to do wasn't always the best idea. Here's my disclosures. I've got no potential for financial or commercial conflict, but over the years I've made a lot of hay pointing out some of the weaknesses of in vivo research, and this has been reflected in lots of nice things, including academic promotions, and I intend to make more hay, part of which I'll be doing today, and I've got some committee affiliations. And to mitigate those potential conflicts of interest, I encourage you to remain deeply sceptical at all times, to believe hardly a word I say. Association is not causation, as I'm about to show you, and I hope I'm wrong, but I fear that I'm not. So for those of you from south of the border, these are the 50 states of the great United States of America, and they're ranked according to their average IQ as determined by the American Psychological Association. And they're color-coded according to their voting behavior in the Bush-Kerry presidential election. So while you and I may believe that there's a link between intelligence and voting behavior, this simply shows an association. My thing is translational medicine, and like Canada, we are a country divided by different languages. This is not a Gaelic road sign, but a Welsh road sign. And you can see it says no entry for heavy goods vehicles, residential site only. And they have got a translation service which allows them then to translate this into Welsh, and what this says in Welsh is, I am not in the office at the moment. Please send any translation work out to get So simply thinking that you're translating isn't always correct. There are many definitions of translational medicine. I would define it as using information from one research domain to guide research in a different research domain. And why that's important for us is that many of the clinical trials which we do claim at least some justification from supporting animal data. And it's the quality of those animal data and the inferences that are drawn from them that I want to talk about. I first got into this over 15 years ago now at the Society for Neuroscience conference in Miami, where I saw this poster, which was later published in a journal called Perfusion. And this is purporting to show the effects of homeopathic doses of arnica montana and low-dose glutamate on infarct volume in a rat. And this is using a standard experimental setup used by many in their field, using half-dose and full-dose glutamate. But when I tell you that half-dose low-dose glutamate is 10 to the minus 120 molar and full-dose low-dose glutamate is 10 to the minus 60 molar, then that tells you two things. The first is that either homeopathy is alive and well, or there's nothing happening here, because those of you familiar with Avogadro's constant will know that there's nothing in either of these columns. And the second more interesting reflection, I think, is the homeopaths even have their columns the wrong way round, because of course 10 to the minus 120 molar should be more powerful as it's more dilute. Moving on to more mainstream work, this is some lovely work done by a colleague in Edinburgh, Ruth Denton, who works for, I'm sorry to say, not my group, but another group. She was interested in gene array studies, and in particular the response of a cell in culture to exposure to staurosporin, which is a drug or a chemical which induces apoptosis. And from this, she was trying to create a pathway of how the effects of staurosporin might end up in the death of the cell, and she put her results from a gene array experiment into this thing called ingenuity pathway analysis, which has got a great name, and you assume does its work. But the 13 genes that she came out with were said to be very closely associated and biologically very important, and she didn't believe it. So being a smart scientist, she said, well, I wonder what happens if I select 13 genes at random and plug them through the system, what happens? And if I do that again and again and again. And she did it 1,000 times with 13 genes selected from the genetic database completely at random. The IPA score, which you can see there, is the logarithm of the odds of those genes being associated together by chance. None of those random selection of 1,000 scored less than 10 to the minus 3, and the median score was 10 to the minus 16. And on such fishing expeditions, millions and millions of pounds of grant-giving bodies' money has been funded because people come up with this, they get a great hypothesis, they go and test it, and all this is telling you is that within our cells, genes work together. And that's all this is telling you, and she was very good to point that out. Who knows about the Atlantic salmon? So good, nobody knows about that. Excellent. So functional MRI scanning is another black box which our well-funded colleagues in neuroscience research developed. We heard a bit about databases for functional scanning earlier. This group had a game they played. Every week you have to trim the scanner to make sure that it's working properly. And they had a competition to see who could bring in the most outrageous piece of organic material to trim the scanner on a Monday morning. And then one day they thought, well, let's not just set up the scanner, let's take this salmon through the imaging protocol and see what happens. So one mature Atlantic salmon participated in the functional study. It was about 18 inches long, it weighed about 4 pounds, and it was not alive at the time of scanning. They couldn't sex the salmon, but they didn't think that was important. And then they administered to the salmon an open-ended mentalizing task. It was shown a series of photographs of human beings with different emotional valence. The people were happy or sad or puzzled or troubled. And the salmon was asked to determine which emotion the person in the photo must have been experiencing. And what they found in the middle of the brain, in the orbitofrontal cortex, were a collection of voxels which lit up, implying that the blood flow to these voxels in the dead salmon was changing. And their conclusion was that either they'd stumbled on a rather amazing phenomena in terms of post-mortem ichthyological cognition, or the technique which was being used was being misapplied and was being applied wrongly by people who didn't really understand what it was that their technique was doing. And they got the Ig Nobel Prize for that last year. So let's move a bit more mainstream. This is Rosenthal and Ford from, I think, 50 years ago now. Rosenthal, who described the file drawer problem. But this was an experiment which he did involving students who were enrolled in a master's program in animal psychology. And at the end of the program, they had to do some experiments to test how much they'd learned. And 12 students were enrolled in the course, and so were involved in the experiment. The experiment was involved a T maze where a rat would walk up the arm of the leg of the T and then have to choose either the left arm or the right arm. And one was dark and one was light, and the dark arm was always reinforced with a food bait, so the animal would learn to turn dark. And they did this in 2 groups of animals, and they were told that there was one group of animals that were maze bright. They'd been bred over many generations in Berkeley to do well in this kind of task, and they were expected to do well, and the other were maze dull. They were just pretty stupid rats, really, and they weren't expected to do well at all. And so they did this experiment over 5 days, and what they found was that the maze bright rats started off better and learned more quickly, and the maze dull rats weren't very good, and they remained not very good, although they learned a bit. And interestingly, when you asked the students what they thought about their rats, those with maze bright rats thought that they were really pretty good. They were nice, cuddly, friendly, didn't try to bite them. And those with maze dull rats, or they all thought their maze dull rats weren't nearly as good. And of course, you've probably guessed the payoff line, which is that there was no difference in these rats at all. They were selected at random from the animal house in that facility. So this is entirely the expectancy effects of the investigators in the study that was done. And so in the early 1960s, one could have said that every behavioral study using animals should be blinded, if only. Because these are the data for a drug called NXY059, which was developed by AstraZeneca and test marketed under the trade name Cerevive because they thought it would make your cerebrum survive following a stroke. And these are like forest plots, but they're on their side. And the reason they're on the side is because the independent variable should always be on the x-axis, because I started off as a pharmacologist and Cochrane have it wrong. But anyway, What you've got in grey is the 95% confidence limits of the overall estimate of how good NXY059 is at improving infarct volume following stroke. And here you can see that those studies which took measures to reduce the risk of bias, that randomized, that blinded the conduct of the experiment, that blinded the assessment of outcome, all gave substantially and significantly lower estimates of how good the drug was in this model than did non-randomized, unblinded studies. And not one of those experiments took all three of these measures to reduce the risk of bias, and the two cited by AstraZeneca in their investigator brochure for the study met none of these measures to reduce the risk of bias. So it's perhaps not surprisingly that 2 clinical trials and 5,000 patients later, NXY059 was shown not to have any impact on outcome following stroke. But it's not just stroke, so we've looked systematically and critically at the animal data testing drugs in models of multiple sclerosis, in models of Alzheimer's disease, in models of Parkinson's disease, and you can see consistently across the piece that high-quality studies give substantially lower estimates of treatment effect than low-quality studies. And these Alzheimer's disease studies are done in the Morris Water maze, where data acquisition is entirely automated. So it's something about the way the investigators are handling or dealing with their animals before they go in to the experimental setup that is completely screwing up their results, and again leading to many clinical trials which have no prospect of success, and we could have said that from the start. I could go on all day, and I'm tempted to, but let me just give you one further example of the quality of reporting. We in our systematic review of animal models of MS, we found almost 10,000 publications, over 1,000 testing the intervention of testing the efficacy and effectiveness of almost 2,000 interventions, and of those, we whittled them down to 203 that we were interested in, but 72 we could not include. 58 did not report the variance of the data. 7 didn't report the number of animals per group. 2 didn't report any error or the number of groups, number of animals per group. 3 were completely uninterpretable, and 2, while they said that it improved outcome compared with control, had no control data. So, as a starting point, 1/3 of the publications in a field can be junked before you begin. So we have been criticized, I think appropriately, that we have started to look at animal data in areas where there's translational failure. If we looked somewhere like cancer or HIV research, then of course animal research would be much, much better, and that was why these fields were successful. So what we have been doing is a random sampling of publications from PubMed. So you just go to PubMed and you search for 2,000 studies by random PubMed ID. Doesn't give you all of animal data, but gives you a fair amount of animal data. And from this, we found 150 publications which described in vivo research. Interestingly, more than half of the publications in PubMed don't describe original research. They describe other people's comments on original research. And what you can see is that the rates of randomization started off at about 15% and have maybe sneaked up to about 20 or 30%. There's hardly any blinded studies. There's no studies which do a sample size calculation as far as we can tell. And there is good reporting more recently of conflicts of interest. And I think that's important because it implies that when journals take an active decision to require reporting of certain things, then they can change the behavior of those writing manuscripts. But of course, PubMed covers a multitude of sins. Everyone knows that there's a lot of rubbish out there in the literature. We need to look at high quality research. In the UK, myself and my colleagues are troubled every 5 years by someone coming along to ask us how good our research is, and we have to submit to something called the Research Excellence Framework, which then produces a league table of institutions with the best at the top. I'm pleased to say that my institution is among the top 5 in the UK. So what we did was we went to those top 5 institutions in the UK and we sampled the research that they'd published describing in vivo experiments in the years 2009, 2010. And this is the reporting of measures to reduce bias in those 565 publications. And what you can see is that for randomization, we get in at about 12% of studies randomized. For blinding, it's about 10%. For stating inclusion and exclusion criteria, it's less than 5%. And we don't really need to worry about sample size calculations because certainly the authors of those manuscripts did not. So even in what is held to be the highest quality in vivo research for from some of the institutions rated to be among the highest quality in the world, the quality of reporting of measures to reduce bias is pitiful. So to summarize, in stroke, where I started, where I thought everything was awful and the world was going to end, we turn out to be the best of everyone involved in vivo research compared with other neuroscience domains, for instance, the random sample of PubMed, and it pains me to say that the top 5 universities in the UK come in last in this league table of the reporting of measures to reduce the risk of bias. One of the measures that's used by those that make these league tables is the impact factor of the journal in which work is published. And it's very important to get one's work published in high-impact journals, because publishing in low-impact journals is no good at all. So what we've done is we've looked over almost 3,000 publications describing in vivo research, which we've identified in the course of a number of different systematic reviews. The association between the impact factor of the journal, and these are deciles of impact factor from low to high going along the x-axis, and the reporting of, in this case, conflict of interest statements. And you can see that higher impact journals are better at requiring authors to report a conflict of interest statement, probably because most of the high impact journals which cover in vivo research are clinical journals which slide it in, and they generally have higher impact factor. Oh dear. Oh dear, oh dear, oh dear. You're probably better off with a sample size calculation if you're in that middling 3 to 4 impact factor range than in high impact. Blinding, well, it's pretty flat. It's about 30% over the piece. These are largely stroke studies, but importantly, if you look at randomization, studies are significantly more likely to report randomization if the impact factor of the journal in which they're published is lower rather than higher. And so this year, the deadline for submission of our Research Excellence Framework this year is in a couple of months' time, and I'm writing to them telling them that all my work is published in journals of very, very low impact, and that's good because it means they're likely to be of higher methodological quality than my colleague down the corridor with 3 Nature papers. I want to talk briefly about publication bias because I think it's interesting. This is across a range of studies in animal models of stroke, of multiple sclerosis, EAE, and of Alzheimer's disease. And you can see that we estimate that there's a 20% rate of non-publication of findings, which leads to an overstatement of outcome of about 30%. And so that's a real and prevalent problem in the in vivo literature. But what about toxicology studies? Because if I'm testing a drug in an animal model, and perhaps I've been funded by industry, or perhaps I've got a patent in this compound, I want the drug to look better than it is. So the bias or the force is pushing me towards reporting large effects rather than small effects. If I'm studying the toxicity of a chemical because I want to be able to make milk for babies out of this chemical, or make the plastic containers that they're fed that milk in, then my bias, particularly if I work for for the Dow Chemical Company, is to understate the effect. And when we look at the literature describing the effects of potential putative chemical toxins on pup birth weight, so you give the chemical to the mother and then you measure the length or the weight of the pups that are born from her litter, you found that the publication bias has the opposite effect. So studies saying that there's a large effect appear to be less likely to be published than studies saying there's a small effect. So these are different patterns of publication bias in different research domains. So in disease models where what you want is an improvement, there's less improvement once you account for publication bias. In toxicology studies where the outcome is harm and you want to show there's no harm, the correcting for publication bias leads you to believe that there's more harm than is actually there in the literature. We've recently published some work on excess significance with Johnny Anitis and others, where we've looked at, across our database of systematically collected in vivo research, and what we find is that out of over 4,000 reported outcomes, based on the exact p-values and the best estimates from meta-analysis of the true effect, then we see that while we would expect to find about 900 positive experiments, in fact we get almost twice that many. So overall, there's a 47% overstatement, which implies that half of what you see isn't true. Now, this is a bit complicated, but let's just assume, if we will, that we're testing a mechanistic hypothesis. So sorry, to go back a stage, the argument that we make in that PLOS paper is that there's selective outcome reporting, that people do an experiment, they measure 5 or 6 or 7 outcomes, and they report the 2 or 3 that confirm their hypothesis, and they just bin the others that don't reach statistical significance. So let's assume that a publication describes six experiments. Let's assume that the mechanistic hypothesis which that publication is seeking to test is in fact true, and let's assume that each of those individual independent experiments using different cohorts of animals are powered at about 50%, and that's being generous because most of our stroke studies are powered, it turns out, at about 30%. Then the probability at least one of those 6 outcomes being found to be positive on testing is 98%. Of at least 2 is 89%, and it falls and it falls and it falls. So by the time you've got 6 tests of this hypothesis, each powered at about 50%, your chance of all 6 of them falling like ducks into a line to get your paper into Nature is 2%. Now, I don't know how many of you read these papers. I have to. None of them have got rates of all 6 being positive at 2%. They're all up at 90 or 100%. So what's happening is that actually if you model it instead with them having done 12 experiments and only reporting 6, then you're much more likely to get positive data. So I think there's good, at least modeling evidence to suggest that what's happening in vivo research testing mechanistic hypothesis is that many, many more experiments are being done than are actually being reported. So my key messages: in vivo studies which do not report simple measures to reduce the risk of bias give much larger estimates of treatment effect. Most in vivo studies in every research domain that we've looked at do not report those simple measures to reduce the risk of bias. On top of that, layered as another complication, publication bias and selective outcome reporting bias further inflate what you think is happening. You cannot assume rigor, even in journals of high impact, and you cannot be confident that people understand what they're doing, even in journals of high impact. And you can only find these things out once you study large numbers of studies. You've got to put together a huge data sets to be able to draw the inferences which I've drawn. And where I think what I'm saying today is relevant for this weekend's purpose, if it's relevant at all, is that any experimental design can be subverted, and usually is, by scientists who usually have the best of intentions. And what's important is to know how to recognize when the experimental design is being subverted. And as people move to adopt new experimental designs, we have to be confident that they understand what's happening methodologically inside the black box of what they're doing, and we have to acknowledge that in 5 or 10 years' time, the next generation of Dave Sacketts will be standing up at conference platforms telling everybody where they went wrong. So when it comes to evidence-based translational medicine, what I would argue is that when you're designing a clinical trial, first of all, you should do a systematic review and meta-analysis of the supporting data, whether that's animal data or not, to seek to find out how powerful the treatment is, what the quality and the range of evidence is, whether there's evidence of publication bias, and what the conditions are of maximum efficacy. And in the Camarades collaboration, we do some of that, and if you follow us on Twitter, there are links to these slides, and even if you look under the hashtag for the Symposium, you can download a copy of these slides if you're interested. And then before exposing patients to hazard in a clinical trial, to do a multi-center animal study to set up the hypothesis that this drug works in this animal model, and do a large enough study to confirm efficacy with robust and monitored conduct of experiments done to the highest standards, with transparent analysis and reporting of those experiments, and deliberately introducing heterogeneity into them to increase the generalizability of your findings. Thank you very much.